Hi everyone, in this video we're going to talk about the powerful sinusoidal AC circuit. First of all, let's talk about instantaneous power in AC circuit. As we talked in last several videos, we can use cosine function to represent our voltage and current in AC circuit, and if we times this together, we can get the instantaneous power in AC circuit. And by putting the two cosine terms together as 2 cosine plus together, we can get this equation. Then by rearranging this equation and this, we can get our instantaneous power in AC circuit looks like this. And while we do this rearranging, it makes the equation longer. If we want to know the power in one period, we do integral for a period. We will see that for this whole part, because it is sine times 2 omega t, if we integral a whole period of sine wave, we actually got 0. So this part is 0, and also if this one times this part is 0. After we simplify those two parts, we can get the power consumed in one period is 1/2 Vm times Im cosine theta minus phi. We can make this equation looks like this. Vm divided on square root of 2 times Im divided on square root of 2 cosine theta minus phi. And this will be equals to Vrms times Irms cosine theta minus phi. And this theta minus phi is the phase difference between voltage and current. Alright, so now we know the power consumed in AC power is Vrms times Irms cosine theta minus phi. In the AC circuit, we also have reactive power. Reactive power is mostly generated by inductor and capacitor. The power can go through the component, but it doesn't actually generate or consuming any power. So it seems like you buy a bag of chips. The actual power is what you eat, but there's a lot of air in the bag to protect the chips, and this part of power, we call it reactive power. The reactive power is Vrms times Irm sine theta minus phi. And we can see we have cosine and sine here, so this has to be something related to a triangle. We put active power and reactive power in a power triangle. We can see this is our power and this is our reactive power, and this is what we call apparent power, Vrms times Irms. And sometimes we also use complex number to represent these three power, which is S equals to P plus JQ. So now let's talk a little bit further about the power factor. The power factor is the cosine value of the angle difference. We know that only inductor and capacitor will generate the phase angle between voltage and current, and also only inductor and capacitor can generate the reactive power. Let's do a little recall. The inductor will create positive phase angle, and the capacitor will create negative phase angle, which means the current is lagging from voltage in inductor and the current is leading, and the reactive power is positive when we have an inductor in our circuit, and the reactive power is negative when we have a capacitor in our circuit. As we know that we use transformer in our power grid, so there's a lot of inductive components in our grade. That means we have a lot of reactive power. What's the influence of the reactive power? If we have two systems, system A and system B, and we both have same amount of power. But for system A, we have 0.5 power factor, which means it looks like this. The power factor is 0.5. That means we have reactive power here. And for system B, we don't have reactive power. Our apparent power is our real power. Our power factor is 1. If our VA equals to our VB, and this SA equals to P divided on cosine theta minus phi, which is P divided on power factor, which is P divided on 0.5, which is 2P. And for system B, our apparent power is P. We know that S equals to V times 2I, and if we have same amount of B, for system A, we got SA divided on B is 2P divided on V, and IV is P divided on V, which means our current in system A is two times of system B. That means the power loss in system A is 4 times more than system B. That's why we are trying to avoid too large reactive power in our transmission system. Before we move on to the question, let's do a quick sum. We talk about 3 kinds of power: apparent power, active power, and reactive power. They are equals to Vrms times Irms, Vrms times Irms times cosine theta minus phi, and this equals to Vrms times Irms and sine theta minus phi. The units for each power is VA, watt, and VAR. The way to describe this 3 kinds of power is power triangle. It looks like this. This is active power, this is reactive power, and this is our apparent power. The angle difference here is theta minus phi. The power factor is a cosine value of angle difference. It is also P divided on S. We have resistor, inductor, and capacitor. And the power factor in resistor is 1, which means the voltage and current are in same phase. The inductor will cause lagging, and the capacitor will make leading, which means our reactive power is 0 on resistor and positive in inductor, negative in capacitor. If we put this in our power triangle, we can see that if we have same power here, for resistor, it doesn't create any reactive power. But for inductor, it gives us positive reactive power, and for capacitor, it gives us negative reactive power. So it will change our apparent power. Alright, let's look at a question here. An inductive load connected to a 100 volt 60 Hz AC source draws 1 kilowatt at a power factor of 0.8. Calculate the capacitor required in parallel with the load in order to bring the combined power factor to 0.95. Let's first draw the circuit. We first have a 120 volts AC source, and we connect it to a load. In this load, we might have resistor, capacitor, or inductor. We don't know that. But we know that now we have our power factor is 0.8. Our power is 1000 watts. By using our equation, we know our S equals to P divided on power factor equals to 1000 divided on 0.8, 1250 VA. We can know our reactive power is S minus P square root equals to minus 1000 equals to 750 VAR. If we plot the power triangle, we now have power equals to 1000 watts, and we have 750 VAR reactive power, and we have 1250 VA apparent power. We apparently doesn't want this high value of reactive power. We can make our power factor be 0.95. So now we know that our new power factor is 0.95, and our new apparent power is P divided on new power factor equals to 1000 divided on 0.95 equals to 1052.63 VA. And by using the same way, we know our reactive power is 328.67 VAR. The new reactive power we calculate is 328.67 VAR. We use capacitor to reduce our reactive power, so that's why we parallel a capacitor arm. And now we are going to calculate the capacitance of this capacitor. So we first need to know the reactive power generated on this capacitor is 750 minus 328.67, which is 421.33 VAR. We know that the current on the capacitor is I equals to C times dV divided on dt, and our I can write as J omega CV. If we calculate the power on capacitor, which is S equals to VI, now we have V times J omega CV, which is J omega C V square. And we also know the apparent power is P plus JQ. So compared to those two, we know that Q equals to J omega C. And we already know Q is this 421.33 and omega equals to 2 pi f. F equals to 60 Hz. So then we know our C equals to Q divided on J omega, which is 77.6. Okay, thank you for watching this video. We'll see you in next video.